Welcome back to the deep dive. And, if you're the kind of person who is insanely curious about how we actually physically build the future, well, you are in exactly the right place today.
Oh, absolutely. This is going to be a fun one.
Yeah, because to hit our global climate goals by 2050, we basically have to build 75 terawatts of solar power, which is just, I mean, from where we are today at about 2.9 terawatts, that is a 30-fold increase.
Right. 30 times more solar capacity than we have right now.
Just let that scale sink in for a second because it's massive. But here's the thing, there's this sort of dirty secret to clean energy. If we try to build that future using the exact methods we use right now, we will literally run out of materials or bankrupt ourselves or, ironically, emit just way too much carbon in the process of actually building the panels.
Yeah, it's a huge issue. We've been conditioned to believe that cost, environmental impact, and material supply are all just, the zero-sum game.
Right, like you want it green. Well, it's going to cost you a fortune.
Exactly. Or, you want it cheap. Grab a shovel because we're going to dig up half the earth to get the materials.
Which is exactly why we're digging into the research today. We are exploring a study that entirely shatters this zero-sum myth. And the paper is titled, let me read the full thing here, Sustainable PV. Optimizing material consumption, cost, and environmental performance through smart sustainability approaches for crystalline silicon solar PV.
That is a mouthful, but it is such a crucial piece of research.
It really is. Our mission today is to understand how this study proves we don't actually have to choose between cheap, green, and scalable. We can actually have all three.
Right, because this study introduces this incredible framework called smart sustainability.
Okay.
And instead of, a manufacturer just obsessing over dollar signs while an environmentalist only looks at the carbon footprint, this framework forces us to step back. You had to look at the entire system all at once.
Like zooming out.
Exactly. And when you pull back and look at the whole picture, you find these, they call them triple optimization points.
Triple optimization.
Yeah, there's specific levers we can pull where the financial costs, the carbon footprint, and the material supply, they all improve at the exact same time.
Okay, let's unpack this. Because to figure out where those levers actually are, we should probably start with the biggest, most obvious part of a solar panel, the silicon.
Right, the core of the whole thing.
Yeah. And making these panels requires just a mind-boggling amount of energy. The study points out that it takes roughly 299 kilowatt hours to manufacture just 1 megawatt peak of solar capacity.
Which is a massive energy budget.
It is. And the vast majority of that energy gets devoured right at the beginning, right? When we're producing and refining the polysilicon.
The refining process is incredibly intense because you're taking raw metallurgical grade silicon
Right.
and turning it into ultra pure polysilicon.
Right.
It isn't just a matter of like throwing it in a pot and melting it down.
Yeah.
It's much closer to distilling water or refining crude oil. You have to break down this raw material at extreme temperatures to extract an incredibly pure conductive base layer.
Wow.
You're growing these massive, flawless crystal ingots. And to do that, it requires an immense, continuous supply of heat and electricity.
But wait, so if I can use an analogy here, it's basically like running a giant energy-hungry pottery kiln.
That's actually a pretty good way to think about it.
But if we're powering that massive kiln, that huge distillation process with a coal plant, doesn't that entirely defeat the purpose? I mean, it takes a ton of power to make the thing that makes the power. You're generating a massive carbon debt before the panel even sees the sun.
If we connect this to the bigger picture, that is exactly the core of the cost-environment synergy that this study highlights.
Okay, how so?
Well, silicon is a fascinating material because it has a very high manufacturing cost and high embodied emissions, but it has almost zero supply risk.
Right, because the Earth's crust is basically made of silica.
Exactly. We are never going to run out of sand. The constraint is entirely about the energy we use to process that sand.
Oh, I see. So the problem isn't the physical material itself. The problem is the electricity we use to make it.
Precisely. Because that upstream refining is so electricity heavy, it's hypersensitive to the local power grid where the factory is located. And the study actually models this out for us.
What do the numbers look like?
So if you manufacture your silicon on a fossil-heavy grid, say, one that's emitting around 1,000 grams of CO2 equivalent per kilowatt hour, the embodied emissions of your solar module spike to over 400 grams per watt peak.
Which is huge.
It's massive. But if you switch that exact same factory to run on low-cost renewable energy, you simultaneously crash both the financial cost of the panel and its carbon footprint.
Wait, let me push back on that for a second. If a silicon factory is sucking up that much juice continuously, like a giant kiln, can a local clean grid even support it? Are we just pushing a local hydro plant or a solar farm to the breaking point just to make more solar panels?
It's a massive logistical challenge, absolutely. You can't just, plug a massive polysilicon plant into some sleepy local grid without totally upgrading the infrastructure.
Right, it would just blow the transformers.
Exactly. And that's why we're seeing this industry trend of co-locating these factories directly alongside massive dedicated renewable energy arrays.
Oh, so they build the clean power plant right next to the factory.
Exactly. And frankly, because renewables are frequently the cheapest source of electricity right now, lowering the emissions by using clean power naturally lowers the manufacturing cost. It's a win-win.
That makes a lot of sense.
But the industry isn't just relying on cleaner power. They're also figuring out how to just need less silicon in the first place.
Wait, how are they doing that? I mean, you can't just make a panel with half the material and expect it to generate the exact same amount of power, right?
Well, you don't use half the material in the final product, but you waste significantly less of it during the manufacturing process.
Oh, okay.
They are physically redesigning the cutting process itself. So when you slice a giant block of silicon, that big crystal ingot we talked about, into paper-thin wafers, you use a saw. And the physical thickness of that saw blade destroys a certain amount of that precious, highly baked silicon. It just grinds it into dust.
Oh, wow.
The industry calls this kerf loss. Kerf is basically the sawdust of the silicon world.
Ah, so all that massive energy you spent purifying the crystal, making it totally flawless, just literally gets blown away as dust on the factory floor.
Precisely. It's a huge waste. So, by moving to ultra-thin diamond wire saws, the blade is much thinner, meaning you lose far less silicon per cut.
Meaning you get more usable wafers out of the exact same ingot.
Exactly.
Which means you didn't have to bake as much raw silicon in the first place. So for you listening, the big takeaway here is that dirty manufacturing of clean tech is an economic problem just as much as an environmental one. The market solves it naturally because wasting energy and wasting silicon eats directly into their profit margins.
Absolutely. So we've established that silicon is an infinite resource that just has an energy problem.
Yeah.
But as you go deeper into the panel's circuitry, the math completely flips.
Okay, what do you mean?
You start running into materials where the manufacturing energy barely matters at all because the physical supply of the material just isn't there in the ground.
Here's where it gets really interesting. Let's talk about silver. Because the price of silver recently surged past, what, $100 an ounce?
Yeah, it's been climbing fast.
And the solar industry is already consuming roughly 23 to 28% of the entire global silver supply, just for solar panels. And I'm looking at this study, and the refining emissions for silver are astronomical. We're talking 361 kilograms of CO2 equivalent for every single kilogram of silver paste.
The carbon intensity per kilogram is terrifying. But what's fascinating here is you have to look at the application.
Okay.
We use such a microscopic sliver of it per panel, we're talking about 12.5 milligrams per watt, that its total carbon footprint on the finished module barely moves the needle.
Wait, really? With emissions that high?
Yeah. It accounts for less than 1.6% of a module's total embodied emissions. The panic around silver has absolutely nothing to do with its carbon footprint. The panic is entirely about absolute scarcity. We just don't have enough of it.
But why are we using so much of it? I thought solar technology was rapidly improving. Shouldn't better, newer technology use less of this rare stuff?
You'd think so, right?
Yeah.
But it's actually the exact opposite.
Diffusely.
Yeah. We're shifting away from standard older panels, what the industry calls PERC cells, over to ultra-efficient next-generation designs. You'll hear acronyms thrown around like POPICON or SHJ, which stands for silicon heterojunction.
Right, the really high-end stuff.
Exactly. These new cell architectures are brilliant at capturing more sunlight and converting it to electricity. But to carry that extra electrical current out of the cell, they actually require significantly more of those silver conductive contacts.
Oh, man. So we're building a much more efficient engine, essentially, but it demands a premium, incredibly rare fuel just to function.
That's a great way to put it. And the crazy thing is, silver isn't even the hardest wall we're going to hit.
Really? What's worse than silver?
When we look at the bleeding-edge technologies this study evaluates, like perovskite on silicon tandem cells, you run into supply chain cliffs that are genuinely alarming. We start talking about elements most people haven't thought about since high school chemistry, things like bismuth and indium.
Bismuth and indium. Why do we suddenly need those? I mean, why can't we just solder the wires together the way we've been doing with basic electronics for decades?
It all comes down to how delicate these new high-efficiency cells actually are. Traditional soldering uses a tin lead alloy, right?
Right.
And that requires temperatures of over 220 degrees Celsius just to melt the solder. But if you hit these new intricate cell layers with that kind of intense heat, they literally physically degrade.
Oh, so the heat destroys the very efficiency you just paid a premium to manufacture.
Exactly. The cell basically cooks itself. So you need a soldering alloy that melts at a much, much lower temperature.
And bismuth allows for that low heat soldering.
Yes, bismuth is the key there. But the indium situation is far, far more severe.
Okay, what does the indium do?
Indium's used to create something called a transparent conducting oxide.
A transparent oxide.
Yeah. In these advanced cells, you need a layer on top that can conduct electricity like a wire. But it also has to be completely transparent. Because if it's not transparent, the sunlight can't pass right through it to hit the silicon underneath.
Ah, so you need an invisible wire, basically.
Exactly. And indium is perfectly suited for this.
Okay, but here's the stat from the study that literally made my jaw drop. It says that if the market reaches just 570 gigawatts of capacity using these new designs, it would consume 878 tons of indium every single year.
Which is an enormous amount. And
Yeah.
keep in mind the scale we talked about earlier.
Right.
570 gigawatts is just a tiny fraction of that massive 75 terawatt goal for 2050.
Exactly. And the total global annual supply of indium right now is roughly 990 tons.
Yep.
Meaning a single sub-terawatt segment of the solar market would swallow almost 90% of the entire world's supply of this metal.
It's a complete, utter bottleneck. And you can't just price your way out of that either. The material simply isn't coming out of the ground fast enough, no matter how much you're willing to pay for it.
So how do we fix it? Because if we want to scale up to 75 terawatts using this tech, the math just completely stops working.
We have to engineer our way out of it proactively before the supply chains snap.
Okay.
For silver, that means actively replacing it with copper plating. Copper is vastly more abundant and much cheaper. And for indium, we have to develop alternative transparent oxides, perhaps using something like doped zinc.
So we basically have to invent our way out of using them.
Yes, we cannot wait until the price skyrockets to a point where the industry collapses. The industry has to innovate away from these critical minerals right now.
Okay, so we've been zoomed way in on these microscopic metals inside the cell. Let's pull back. Let's look at how these panels are physically mounted out in a field in the dirt.
Good pivot. This is just as important.
Right, because fixing the silver problem inside the panel doesn't matter if we install the panels in a way that tanks the whole system's overall efficiency.
Exactly.
To me, it's kind of like buying a cheaper, lighter car to save money on the steel chassis, but the engine is so underpowered that it gets terrible gas mileage.
Right.
Sure, you saved money on the structural frame up front, but you end up buying twice as much fuel over the life of the car. You optimized a component, but you completely ruined the system.
That analogy perfectly illustrates what the study calls the system-level trap.
The system-level trap.
Yeah. We often optimize a single part of a solar array without realizing the cascading effects it has on the whole operation. So the study compares 3 types of setups for utility-scale solar farms.
Okay.
You have fixed tilt, where the panels just sit at a permanent angle facing south. You have single-axis tracking, where motorized steel racks physically tilt the panels to follow the sun across the sky all day.
Like a sunflower.
Exactly.
Hmm.
And then you have east-west mounts, where the panels are pitched like a tent, packed really tightly together, with half facing east and half facing west.
And if you're just looking at the physical materials, east-west mounts sound incredible, right?
Yeah.
Because they pack in so tightly together, you save a ton of structural steel and aluminum per megawatt you install.
Exactly. On a spreadsheet that's just tracking structural materials, east-west looks like a huge, obvious win.
Hmm.
But here's the trap. Because they are essentially locked into that static tent shape, they aren't optimally facing the sun for the entire day.
Right, because the sun moves.
Yes.
Yeah.
So their overall energy yield, the actual electricity they produce, is significantly lower than a tracking system.
So how does that apply to the solar field in the long run? Like, why does that matter if the racks were cheap?
It means we have to completely change the metric for success. We cannot measure sustainability by installed capacity.
Meaning, just how many megawatts of panels are sitting out in a field?
Right. We must measure it by electricity actually delivered per kilowatt hour over the system's entire 30-year lifetime. Because those east-west mounts yield less power, you actually have to manufacture and install far more total solar panels to hit your grid's energy target.
Oh, wow.
Yeah,
So wait, to save some basic structural steel on the mounting racks, you end up having to build thousands of extra panels,
precisely.
which means you are burning through significantly more of that hyper-rare silver, the indium, and the highly processed, energy-intensive silicon just to make up for the lost power.
It's a terrible trade. You sacrificed the highly constrained critical minerals just to save on the most abundant structural materials on Earth.
That is wild.
It is. Single-axis tracking systems use a lot more steel up front for the motors and the moving racks, but they generate so much more electricity over their lifetime that they mathematically minimize the total amount of critical minerals used per kilowatt hour.
So the absolute best way to save our rare silver supply is to put the panel on a heavy moving steel tracker.
Yes, exactly.
But what about the frames holding the actual glass panels together? Because the study spends a lot of time on this dilemma between aluminum and steel for the module frames.
Right. The frames are a huge material sink.
Yeah.
Currently, about 95% of all solar module frames are made of aluminum.
Okay.
And it makes sense, right? It's lightweight, it doesn't rust easily.
Yeah.
But the solar industry is already consuming up to 3 to 4% of the entire global aluminum supply just for these frames.
Just for the frames.
Just the frames. And smelting primary aluminum from scratch is brutally carbon intensive. It emits about 65 grams of CO2 equivalent per watt.
Well, wait, can't we just use recycled aluminum? I mean, if we just melt down scrap, that's way less energy, right?
It is. It drops the emissions dramatically, down to about 8.7 grams. But if we're scaling to 75 terawatts, there simply isn't enough high-quality aluminum scrap in the world to feed that beast.
We just run out of cans and old car parts.
Exactly. We'd exhaust the secondary market almost immediately.
So what's the alternative then? I mean, we can't exactly frame them in wood. Do we use steel?
Steel is actually the most viable alternative. It's much heavier, which obviously makes shipping and physical handling on the job site a lot harder. But steel scales infinitely better over the long term.
Because there's more of it.
Right. And as the broader heavy industry transitions to what they call green steel, using hydrogen instead of coal to run the blast furnaces, the carbon profile of a steel solar frame becomes incredibly competitive. But the best choice shifts constantly. It totally depends on carbon taxes, the availability of green steel, and how clean the local grid is.
So with all of this, I mean, the massive energy needed to bake the silicon, the absolute panic over the indium supply, the heady steel tracking systems we have to build, I have to ask a very pragmatic question here.
Go for it.
For you listening, you might legitimately be wondering, is the juice actually worth the squeeze? If we put all this energy and material in, do these massive arrays generate enough power to pay back their own existence? Or are we just spinning our wheels on a giant green treadmill?
It is arguably the most critical question of the entire energy transition. And scientists measure this using a concept called EROI.
EROI, energy return on investment.
Exactly. It's essentially an efficiency ratio for human civilization. You take the total usable energy a solar system delivers to the grid over its 25 or 30-year lifetime, and you divide it by every single ounce of energy invested to build it.
So the energy to mine the silver, bake the silicon, smelt the frames, and truck it to the site.
All of it. Total energy out divided by total energy in.
Okay, so if I put 1 unit of energy into building the panel, how many units of energy does it hand back to me over its life?
Right. And to put that ratio in context, energy economists estimate that to maintain a highly complex modern society, meaning hospitals, universities, the internet, global logistics, an energy source needs to deliver an EROI of at least 10.
Okay, so a 10-to-1 ratio.
Right. You need a 10-to-1 return just to keep the lights on and keep human progress moving forward. Anything less, and society starts going backward.
10-to-1 is the baseline. So how does solar score on that test right now?
The data is incredibly encouraging, actually. Global solar PV EROI is on a massive, sustained upward trajectory.
Really?
Yeah. Back in 2015, the global average was hovering right around that threshold of 10. But thanks to the mechanisms we've discussed today, like the thinner silicon wafers cutting down on energy waste, the clean grids powering the factories, the advanced tracking systems maximizing sunlight, the EROI is projected to hit between 27 and 37 by the year 2050.
Wait, a 37-to-1 return on energy? That sounds fantastic.
That's massive.
But wait, let me push back on this. The sun sets every single day. If we're scaling to 75 terawatts, we can't just power the grid when the sun is up.
Very true.
We are going to need a mountain of batteries to make this work at night. Doesn't mining the lithium, processing the cobalt, and manufacturing all those heavy chemical batteries completely destroy that 37-to-1 score?
It's a very valid concern. You absolutely cannot have a reliable grid without storage. And adding massive battery banks does introduce a penalty to the system's overall efficiency. The study actually calculates this. Integrating heavy battery storage shaves about 10 to 20% off that EROI score because of all the embodied energy required to manufacture the chemical storage.
Man, that's a massive haircut. That drags the score down significantly.
It does. But the underlying efficiency gains in the solar panels themselves are actually outpacing that penalty. Because battery manufacturing is also scaling up and getting more efficient, the study concludes that even fully battery-backed utility solar systems will stabilize at an incredibly healthy EROI of 30 to 35 after the year 2035.
Oh, wow.
Yeah. Even with the batteries, the system generates more than triple the baseline energy needed to run a modern society.
That is genuinely amazing. So what does this all mean? If we pull all of this together, what does this actually mean for how we build the future? To
Yeah.
reach that mind-bending goal of 75 terawatts, we can't just chase cheapness, and we can't blindly chase greenness. We have to pursue triple optimization. We have to decarbonize the power grids to make refining silicon both clean and cheap. We have to proactively design away our addiction to rare metals like silver and indium before the physical supply chains literally run dry. And we absolutely have to measure our success by the actual kilowatt hours delivered over a lifetime, not just by how many panels we can stick in the ground on cheap aluminum racks.
That is the ultimate essence of smart sustainability. It's this realization that environmental performance, cost reduction, and material security are not competing forces.
They aren't a zero-sum game.
Exactly. When you understand the mechanisms and engineer the system correctly, improving one naturally improves the others.
It fundamentally changes the paradigm of the energy transition. It goes from a story of sacrifice to a story of incredible engineering.
It really does.
And as promised, I want to properly bookend this conversation by citing the foundational text for today's journey. All of the frameworks, the supply chain modeling, and the EROI math we discussed come directly from the brilliant work in the study titled Sustainable PV. Optimizing material consumption, cost, and environmental performance through smart sustainability approaches for crystalline silicon solar PV.
And as we close today, I want to leave you with one final thought to explore on your own.
Oh, I like this.
We have focused intensely today on the physical materials going into these terawatts of solar panels. But we actually pull this off, and we build 30 times more solar capacity by 2050. It creates an entirely new geopolitical reality.
How so?
Well, for the last century, global power was dictated by nations sitting on vast underground reserves of oil and coal.
Right.
What happens to the global balance of power when energy dominance shifts away from what you have buried under your soil and shifts toward the nations who control the intellectual property and the complex recycling loops of silver, bismuth, and indium?